Welcome, class. In our last lesson, we looked at completing the square to solve quadratic equations. Today, we're going to be using that procedure for another purpose. Today, I'm going to be completing section 9.2 and 9.3. We're assigning that today, Monday, April 20. It'll be due this Friday, April 24. So it gives you a rough idea of what we're going for here. As I mentioned, last lesson we used completing the square to solve. We said this always works, whether it was factorable or not. Just reviewing the procedure, I made this one more of a challenging one, where the leading coefficient is not a 1, and our x coefficient is not an even number. If you recall, we would begin by factoring the 3 out. Taking a 3 out of the 5 meant it changed it to 5/3. Notice if I take 3 and multiply it times 5/3, you would get 5. So this is a correct way to factor it out. Now I need to take the 5/3 times 1/2 and then square that answer. So here I took that 5/3 times 1/2, that's cutting it in half, gives me 5/6. Then I take the 5/6 and square it, which gives me 25/36. That's the number that I am going to add in here to make it a perfect square. I completed the square by adding that number. But when I add that number, it really is this number times 3. 3 times 25 actually gives you 75/36. So that would be the number that I need to add on the right side to keep my equation true. This then, in parentheses, is a perfect square. It factors into x plus the square root of 25/36, which is 5/6. You could multiply that parentheses times itself and you would get the top parentheses. Here I just combined the negative 36 over 36 plus 75 over 36 to get that fraction. My next step is to divide by 3. So if I divide by 3, a lot of ways I could do that. I just took 39, divided it by 3, which gave me 13. Here when I divided by 3, it canceled out. Then we're basically in that quadratic form. We take the square root of both sides. Notice here I took the square root of 36 to get 6, but I left the radical up in the numerator, and I get my answer. Somewhat of a complicated procedure, not one that we would enjoy doing all the time. But we're going to do it just one time now in general form. The reason for that is because this procedure works with all those equations in that form, as long as a doesn't equal 0, we now do the procedure on the general form, ax squared plus bx plus c. To help you kind of follow along, I'm going to put the other form over here. And I hope that you'll be able to kind of see as I'm moving along. Here I have ax squared instead of 3x squared. This is the one we just did. Bx instead of 5x. C instead of 1. My first step was to factor the 3 out. So I factored this a out front, just like I did the 3 over here. Here I got 5 over that 3. Here I get b over that a. I move the negative c across and decide how I'm going to add to both sides. If you remember, I took the 5/3 times 1/2 and squared it. Here I take the b over a times 1/2 and square that answer. That answer then, right here, is what I need to add in both of these blanks. just like over here I added these two. Then, as it was over here, this left side was a perfect square. This will also be a perfect square. I also divided by a in this particular term. So I divided by a and factoring it. That a turned up and made this into an a squared. Then I take the square root of both sides. And just like I could take the square root of 36 here to get 6, I can actually take the square root of 4a squared to get 2a. So I end up with both denominators being 2a, but the radical stayed in the numerator. Then I bring this fraction across and combine it. And I get a very important formula for us. It's referred to as the quadratic formula. It's a formula you should know by memory. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Notice the a in our formula is the coefficient of x squared. The b in our formula is the coefficient of x. The c in our formula is the number there by itself. We have to be able to correctly identify a, b, and c. For example, over here, a would have been 3, b would have been 5, c would have been 1. We'll need to be able to make those identifications in our problems. If you don't have this formula copied down in red, make sure you do so. If you have to pause to copy it down, but it's also one you want to have memorized. We're going to use the formula now. Notice a is 3, b is 4, c is a negative 5, because there's a negative in front of that that comes along with the c. So here's my formula. So b is a positive 4, negative b would be a negative 4. And I have no idea why I put a 5 there. I apologize. That should have been a negative b. I am so sorry. That should be a negative 4 there. Because b was a positive 4, so a negative b would be a negative 4. Everything else you can see I plugged in, but this negative 4 is a total mess up on my part. The 4 squared is 16. 2 negatives will make a positive. 4 times 3 times 5 is 60. 16 and 60 makes 76. The 76 I can take and break it apart into radical 4 times radical 19. The radical 4 becomes a 2. So this ends up to be a negative 4 plus or minus 2 radical 19 over 6. And again, just flat out messed up on the negative b. I would like you to try some here. I'm going to put the formula up here just in case you forgot it. First thing you should do is identify your A, B, and C. So in this problem, A is 1, B is a negative 3, C is a negative 6. Go ahead and substitute into your formula now and do that for all three of them. I'm going to give you a head start and then we'll follow up. Notice again, sometimes I get some nice integer or rational numbers. They're real number answers. Other times I get a positive radical, so they would still be a real answer, but it would be irrational. And sometimes I get an answer containing I, or a complex answer. That is going to be a key for us in this upcoming part. But this gives you an idea how we use this formula to solve. Notice it will always work as long as the A is not equal to 0. I'd like you to notice when we use that formula, sometimes, as I just mentioned, we get nice rational integer, sometimes answers, but they're certainly rational and real. Sometimes we get a radical in them, which is irrational, but they're still real. Sometimes we get answers like this, where I have a negative radical, which gives us an I, or a complex. I would like you to notice that the type of answer we get is really determined by that radical right up there. Because that's a rather important part, the value of that b squared minus 4ac determines what type of answer we get. Because that's an important part, we give it a name. We're going to call it the discriminant, because it discriminates between what type of solutions we get. So the discriminant, b squared minus 4ac, is just part of the overall quadratic formula. We've done these often enough to know that there are certain types of values that the discriminant will equal that determines the type and how many solutions we get. For example, if the discriminant is positive, then there are two real solutions. They might both be rational or irrational, or one of each. But you're going to get two real solutions. Examples like those, or something like that and that, both of them were real solutions. We didn't get an example like this, but if the discriminant turned out to be 0, then we get one rational, real solution. It's often referred to as a double root. I'm going to speak a little bit more about that in just a moment. If the discriminant is negative, an example would be right here is a negative 25, then I get an I in my solution. Excuse me a second. Yeah, I gotta call you back. I'm on a video right now, okay? Okay, talk to you later. Bye. Sorry about that interruption. If the discriminant is negative, like a negative 25, it was in this case, then I get an I, which is a complex solution. We should know what these three results produce. Again, real quickly, if the discriminant is positive, I get two real solutions. The discriminant is 0, and I have one real solution. If the discriminant is negative, then I have two complex solutions. You need to know those and be ready to answer for those. Graphically, these types of equations that I've been looking at here graph to produce parabolas. And we've talked about parabolas before. But for this first one, two real solutions, it means that the parabola crossed the x-axis in two places. The parabola might have opened down but it crossed in two places. That's why I had two solutions. Each place where they crossed was a solution. They might have been rational or irrational, depends on the problem. But this is where the discriminant was greater than 0. When the discriminant equals 0, what it meant was the parabola touched the x-axis in only one spot. This would have been typically something like this. Had you factored it, say sometimes you have a double factor like this. That would have meant my original looked like that. Sorry, I ran out of space. That would mean this solution would have been 8, and this one would have been the same number. We call that a double root. It means the parabola touched it only once, only one answer. In this case, the answer was 8. If the discriminant is negative, the discriminant is less than 0. Here it was positive, here it's less than 0, negative. That means that the parabola did not touch the x-axis at all. There were no real solutions on the x-axis. That gives you a little bit more of a visual of what's going on. For our last slide here, got kind of a short lesson today. We would like to indicate the nature of the solutions. What I mean by that nature is this, going back to here, 2 real solutions, 1 real solution, 2 complex solutions. 2 real, 1 real, 2 complex. Okay? So looking at that then, I'm going to do that by looking at the value of the discriminant. So I'm going to first just calculate the value of that discriminant, b squared minus 4ac. b squared would be 5 squared minus 4 times a, which is 2, times c is 1. I get 25 minus 8. That turns out to be 17. 17 is a positive discriminant. If it's a positive discriminant, that means that I have 2 real solutions. So to answer this question, the directions, this is my answer. I don't need to actually get the exact answer using the whole formula. They just wanted the nature. So this describes the nature of it. Take the discriminant again. b squared would be 5 squared minus 4 times a, which is 2, times c, which is 10. Get 25 minus 80. That turns out to be a negative 55. Because it's negative, I have 2 complex solutions. When it was positive, like 17, I had 2 real. Negative, I have 2 complex. That would be my answer. Here's one, that if I calculate the discriminant, b squared minus 4ac, it's going to be 8 squared minus 4 times a, which is 1, times 64. That's going to be 64 minus 256. I'm afraid I can't give the exact number off the top of my head, but I know it'll be negative. So I have 2 complex solutions. These are our last 3. The discriminant, b squared minus 4ac. 4 squared minus 4 times 2 times 2 gives me 16 minus 16, or 0, means I have 1 real solution. b squared minus 4ac, I get 5 squared, minus 4 times negative 3 times negative 1 gives me 25 minus 12 gives me 13. That's positive. 2 real solutions. And our last one, b squared minus 4ac. b squared is 10 squared minus 4 times 5 times 5. That's 100 minus 100 gives me 0. I have 1 real solution. You'll be asked to give the nature of solutions in your assignment. For the most part, pretty easy lesson, as long as you can plug into a formula and evaluate the answers. That's all I have for today, so it's a nice short lesson. I'm going to stop here kind of quick. And if I can find the finished icon here.